So we're going to take a peek at the Quiz 8 preview. I know at the top it says 7, but again, what else is new when I mislabel something here? So simplify the following. Okay, big stressor up here at the top. First two problems. There's a plus in the middle. There's a minus in the middle. Do not multiply this out. Do not distribute. Do not make a box. Don't do any of those things. We're just combining like terms when there's plus or minus in the middle. And we always want to go in standard form, which is greatest degree down to least. So I look around and I say, okay, x to the fourth is the biggest one I see. That's the only one of those, so that one's set. And then I just start working my way around. 8 minus 10. I got to pay attention to the sign in front of each term. Minus 2x to the third. Again, no messing with exponents when you're adding and subtracting. Minus 7x squared. Then I've got 2x terms. 1 minus 5 is negative 4x plus 1. Done. Okay? Keep life simple. Just combining like terms. The only difference in number 2 is that now I'm subtracting my second quantity, my second set of parentheses. I am a very big proponent of taking the extra time and actually writing this step out, where I'm distributing that negative to each of the terms in the second set of parentheses. So basically we're just changing the signs on those and then combining like terms. So again, look for the biggest one to start with. Then my squareds come next. Then my single x term. And finally, my constant terms. So again, those first two should probably be two of the easier ones that you see on the quiz, as long as I'm careful with my details. Now when I get to 3 and 4, totally different story. Now I do have to multiply through. And I know some of you like just taking the 2x and distributing it through, and then taking the negative 3 and distributing it through, and then combining like terms. Others of you, and again, I'm a proponent of this myself, is you kind of use a little bit of an organizational tool to do the same thing. The reason I like this is because all of my like terms are going to get grouped together, and there's no chance that I'm going to forget about one of the terms. So again, now we're multiplying. So you multiply the coefficients, add the exponents, because that's my exponent rules. So multiply, coefficient, add exponent. And again, little things. Negative times negative is positive. Those are the type halves that a lot of people miss here and there, and then it ends up giving them a grade they're not really especially thrilled with. But again, the nice thing here is now my first term will always be up in the corner, and then each diagonal gives me the next term. But again, it tests your patience and your attention to detail. Now I will warn on 4. This is one of those that I will probably bang my head against the wall if I see an answer tomorrow of x cubed plus 27 and that's all there is. I'm just going to start whacking my head on whatever's close. You can't just distribute 3 and call this done. Because remember, what this actually is is 3 of those. Now, could I use the pattern that we talked about back when we were doing these? Sure. Okay, I always have a couple of people that'll do the pattern, but the rest are like, or they make it x cubed plus 27. So, what you would do if you're not a pattern person is you would take them a pair at a time and you'd multiply it out. So here, FOIL, box, doesn't matter. just to save us a little bit of space here, that would be what I'd get when I FOIL or box that out. Because again, I'd have my first, my outer is negative 3x, and so is my inner. So that's where this is coming from. And then negative 3 times negative 3 is 9. And what I do with that then is I have one more binomial term, my x minus 3, that I'm going to multiply by. So again, multiplying, you add exponents. So I go ahead and multiply these. Now again, is the pattern faster? Yeah. But again, if you don't have a grip on the pattern, what good does the pattern really do you? So again, once I multiply to fill the box, we're just combining like terms. No more messing with exponents. Negative 3 and negative 6 is negative 9, x squared. 18 and 9 is 27x minus 27. And again, for those of you that are saying, now you keep talking about this pattern, I don't remember, how'd that pattern work again? The pattern when you're dealing with a cubic, we'll just kind of make note of it here so you can see it, would be a cubed plus 3a squared b plus 3, oops, not when it's minus, Harty. Silly man. Squared plus b cubed. My a value would be the x. My b value would be the 3. And I'd plug it into that, and I could get the same answer. But again, if not, that's going to be your other option. Okay? So when we're thinking about those, we've also got, again, evaluate. Find f of negative 3. In other words, take whatever value is in the parentheses, plug it in for the x's. So like here, negative 4 times negative 3, because that's what I'm plugging in for x, it'd be 12 plus 3. So I'm like, okay, 12 plus 3 is 15. Absolute value bars don't do a whole lot for a positive number. It's just the negatives it really changes a value on. So negative 2 times 15 is negative 30, and that would be my function's value at negative 3. Straight substitution is all you're doing. Now sometimes, though, that's going to be a little bit more interesting. Now here, there's a couple of places I need to be careful. One is, you don't multiply and then go to exponent. That's not how order of operations works. Cube the negative 1 first, which is negative 1, then multiply it. So negative 1 times negative 2 is 2. Negative 1 squared is 1, times 5 is 5. And add those up. Or you could just put it in the calculator. Again, doesn't matter. Either way is going to be fine. Like I've said before, if I do something, you're like, wait a minute, what are you doing? Holler at me. We'll get that set. Well, unless you're at home watching this, then hollering at me probably won't do you much good. So then we start applying this a little bit. Senior class is selling t-shirts for a prom fundraiser. The class is selling the t-shirts for $12.50 each. The shirts cost the senior class $60 for the design print plus $4.50 for each shirt. Okay, write the profit function, which is always going to be my revenue minus my expenses. My revenue, how much money am I taking in sales? Well, if we're selling shirts for $12.50 each, here's where I have to be careful. I'm getting $12.50 for a shirt, but I don't know how many. When you see a magic word like each, we have to represent that somehow. So we represent that with X or whatever other variable you'd like to use there. So I'm making $12.50 times the number of shirts. But there's expenses involved. So we're going to subtract those. They cost us $60 for the design, so whether if I make one shirt or 1,000, I have to pay that $60. Plus $4.50 for each shirt. And here's the one danger here. What's one more thing I need to add into this little equation right now, or I'm going to get myself in trouble? Parentheses. Because if I do it right now, I'm going to be subtracting the 60, but this is going to keep adding. That doesn't make any sense. I have to subtract the expenses as a whole, so I have to have the parentheses there. Because that means that minus, or that negative, is going all the way through. So I get there and I say, okay, so I'm going to have $12.50 minus $4.50, which would be 8x, and then minus 60. And that would be my profit function. I'm going to make $8 a shirt minus $60, because that's the expense of my design print. So find the profit on 125. Okay. Substitute 125 in for x. Again, this is just a label. I'm not solving for p. 8 times 125 is 1,000 minus 60. Looks like I'm making about $940 here. But again, you're just substituting. Keep life simple. We just do some different things with labels. So then we get back to the new stuff here. We have f of x and g of x. Write an expression for each function. State any domain restrictions. Now remember, our domain restrictions, no 0 in the denominator, and I can't have an even indexed or an even root that's negative, so it has to be greater than 0. So f plus g of x, again, just means I'm doing f of x plus g of x. In other words, combine like terms. Well, Harty, there's not any like terms, because I got 4x squared and 2x and 7. Well, then all I have to do is write 4x squared plus 2x plus 7. Nothing's alike. I'm done. Like, it's really that, yeah, it's that straightforward. F times g of x, again, means f of x times g of x. Not f times g and then multiplying it by x. Not what we mean. So we're going to do 4x squared times 2x plus 7. And we're going to distribute. 4 times 2 is 8. 2 plus 1 is x to the third. 4 times 7 is 28x squared. No more like terms. I'm done. But when we get the open circle in the middle, f of g of x, again, whatever comes second is what we're plugging in. So you're like, okay, so g of x is this. So I want to find f of 2x plus 7. In other words, plug 2x plus 7 in where the x is here. So 4 times, I'm taking the x out and replacing it with this. 2x plus 7 squared. So, reminder, can't just distribute the 2. Doesn't work that way. So, we do a little work off to the side here because we're kind of cramped for space. Ignore the 4 for right now. So, you've got 2 of these, and again, you could use a binomial formula. You're like, wait a minute, binomial formula, what do you mean? Where I take the first term squared, and if you want to box this out, you could. So I'd have my first term squared plus 2 times the product of those terms plus my last term squared. This sheet is stuck. There we go. Again, you also could do this though. And I like to give you options because some of you like formulas, some of you like visually seeing all the parts. So if I do it with the formula, I'd have 4x squared. 2 times 2 is 4 times 7 is 28x plus 49. I would get the same thing if I did the box. 14 and 14 is 28. But then I got to multiply it by 4. So basically, I take this, I distribute a 4 through, and get 16x squared plus a whole lot x, 212x, plus 196. Take it in pieces. You've got to do the function first, and if there's ever a number outside of that, that's what I take care of last. Always work inside out. And if it would have been g of f, we just would do the opposite. We'd plug f into g, which actually been a little easier that time. So we kind of keep popping through, and we're like, okay, put this back over here in case some of you are still jotting things down. F divided by g of x means f of x divided by g of x. Move this down a little so I can see my functions. So I've got 4x squared over 2x plus 7. Now you'll notice we haven't talked about any domain restrictions yet. But again, I haven't seen any fractional exponents. I haven't seen anything with a denominator so far. Ooh, I do now though. This would be my f of g of x, but I have to make sure the denominator doesn't equal 0. So I do a little side work. I take my denominator. I set it equal to 0 because I wasn't silly enough to try and cancel these. They're locked together. Don't forget. Minus my 7 over and divide by 2. Since all it says is state any domain restrictions, it doesn't say state the domain, I don't care if you just say x can't equal -7/2. That's fine. If it asked you to state the domain, we'd be doing -infinity to -7/2, and then union that with -7/2 to infinity. But we're only going to do what the directions ask us to do. We're going to keep life simple. But again, always look, fractions and even indexes or square roots are the main things you're looking for a restriction there. 12 kind of snuck it in here. Let f of x equal 4x squared minus x, g of x, x minus 8. What is f minus g of 2? Again, f of 2 minus g of 2. You're like, well, could I do this minus that first and then plug in the 2? You could. But I have a feeling you might want to multiply it if you wait, so don't do that though. So if I plug in the 2 for each of these, I'd have 2 squared is 4 times 4 is 16 minus 2. That would be 14. So that's my f of x, well, my f of 2. My g of x is just plugging 2 in there. 2 minus 8 is -6. But be careful. I'm subtracting f of x minus g of x. 14 minus -6 is like 14 plus 6, or 20. Be careful, be careful, be careful. And then a couple more things with our function notation, and then we'll get back into some of our exponent rules and things. Little dot, or just together as multiply. So I'm going to plug 8 in for x in both of these and then multiply those two solutions together. So we're doing P of 8 times Q of 8. So 3 times 8 is 24, minus 6 is 18. So that's my P of 8. My Q of 8, again, square the 8. Don't multiply first. Square the 8 is 64, times 2 is 128, minus 3 is 125. Do I trust myself to do this in my head right now? I should, but I'm not. I think it's 2250, but I'm too afraid. Dang, I had it. So 2250, and that's it. But again, open circle is of Q of P of negative 3. In other words, plug in negative 3 to the P, and then plug that into Q. You're like, dang. So 3 times negative 3 would be negative 9. Minus 6 is negative 15, but it's the absolute value. So the absolute value of negative 15 is 15. So that's what P of negative 3 equals, so that's what I'm going to now plug into Q. So I'm going to do 2 times 15 squared minus 3. And again, just follow order of operations. 15 squared is 225, times 2 is 450, minus 3 is 447. Again, it's all about order, inside out, and not trying to do all these multiple steps at a time and get yourself in trouble. So again, nothing too bad going on there. Down at the bottom, it's all about exponent rules. This 5 goes through to everything. Yes, even the y where I don't see an exponent. So let's clean this up here for a second. So negative 2 to the 5th. What do I do to exponents when I'm going power to power? Multiply. So negative 3 times 5 is negative 15. Y to the 5th, z to the 10th. So here's what I've got to deal with at this point. You're like, why are you putting it all over 1? Because I see negative exponents, and we know when we have negative exponents, we have to flip them. Negative 2 to the 5th. Reminders. That's not a negative exponent. It does not flip. Second thing, this is not negative 2 times 5. It's negative 2 times negative 2 times negative 2 times negative 2 times negative 2, which is negative 32. Again, not a negative exponent. That's a negative exponent, so that gets to go down to the denominator. But neither of my last two terms have negative exponents either. So that's as far as I can go. And I'm done. So again, it's a patience issue. 16 is about 50-50, and I think some of you will do it. Some of you will say, hey, that's a negative exponent. I can just flip this whole fraction and then make it positive. And some of you, that would flip out. So if we just kind of keep to the same game rule that we're going to distribute the exponent through, and then we'll just deal with the negative exponents when we have to. You're like, dang, they're all negative. Okay, so they all flip. So any term that's in the numerator with a negative exponent goes to the denominator, and if it's in the denominator with a negative exponent, goes up to the numerator. No like terms to put together, I'm done. And ready to roll. And that's basically what I'm going to do with all of these. Same idea going with 17. And again, it's better to take the extra time and see the step, then deal with it. This is flipping down to the bottom and becoming 5 squared, which is 25. Do I have to flip a to the 4th? No, it has a positive exponent. B to the negative 2nd? Yep. that goes up. No more negative exponents, no like terms. I kind of get the point here. You're like, Harty, are you doing a little overkill here? 16 through 18, it's like all the same thing, and you just keep having us redo it and redo it and redo it. Well, this is something that tends to give people issues. So again, the more experience with it, the more we take it head on, the more likely we are to remember to do it when we have to. So here, 3 to the 4th goes down below. So that would be 81. P goes down, M goes up. Ready to roll. But you've got to remember your exponent rules. Power to power, we multiply. If you're just multiplying, then you're going to add those. So again, lots of things to keep track of, but not impossible. So you're like, okay, not so bad. So what else you got for us? Yes, sir?
Actually, on the other side of the page, for 17 and 18, you put the negative, like the normal value, negative 25 and negative 81 on the bottom. But you left the negative 32 on top.
Okay, let's talk about that for a second. So why am I getting a negative here, but these aren't? And here's the reason. When you're taking a negative number to a power, if it's an odd power, like 3 or 5 or 7 or something like that, when you think about it, what's actually happening here? So if I have 5 of these, for every pair of negatives I have, it becomes positive. Negative times negative is positive. Negative times negative is positive. But then I still have this one at the end. So I end up with like 16 times negative 2. So I actually end up with a negative answer. When I get an even exponent, so let's take this 3 to the negative 4th, for instance. So when that flips down, it becomes 3. And again, it's not a negative. 3 to the 4th is just 3 times 3 times 3 times 3. Well, with no negatives, I'm still getting a positive answer, because when we do the flipping and stuff, that just affects the exponent. It doesn't affect like the answer. It doesn't make like a positive number become negative, is what I'm trying to say with that. So, and if in doubt with the number part, you always can go calculating once you get it flipped to see how that works. All right, sketching on the back. Couple of things I would hope you would know, but if not, we can adjust. We know we're going to have a parabola. It's a quadratic. We know it's opening down because of the negative. What I need here is a vertex. I would hope you'd remember, if there's just a number out here, that your vertex is just going to be shifted up 5. But what if you don't remember? Is there still a way? Is there still hope? Yes. A couple ways there's still hope. The easiest one would be to say, oh yeah, when I'm trying to find my vertex, my x value is negative b over 2a. But wait a minute. When I do these, my b value is what's in front of x. There is no x term. You're right. My b value would be 0. So my x is 0. So if I went to look at that then, and I know what the x value of my vertex is, as always, I can get my y value from here, and I see the symmetry for the rest of my points. Now, can I get away with doing a sketch? In some cases, yes. In this case, not quite so much, because if I just went with a straight sketch, my vertex value may be off. You're like, but it's just a sketch. Why does it matter? You'll see in just a second here. My domain, x values left to right, forever going out to the left, forever going out to the right. So that part's easy. The range is a little different though. It doesn't go down forever, up forever. It does go down forever. But how high do we get? Oh, the vertex. Okay, vertex y value. 5. That's why I needed to know where the vertex was. So that's something I have to keep an eye on. Also, okay, my end behavior, for my x's, I'm always going to have one that approaches negative infinity and one that approaches positive. Doesn't matter the order that I put them in as far as that goes. But then just remind yourself, whether it's our little chart we talked about before with odds and evens and lead coefficients, but you're going to have a picture to look at, so it's not going to matter as much. So for instance here, as x goes left, what's happening to y? That's the basic question. Well, it's going down. Okay, well, when something goes down, it's going towards negative infinity. Oops, except that's right. Ha ha ha. People watch this at home are going, okay, this guy thinks that's left. We're in trouble. You're right. You would be in trouble. Fortunately for me, though, I get bailed out because when I actually do look at the arrow that's going left, it is going downward towards negative infinity. But now let me do the second part of it correctly. When my graph is going to the right towards positive infinity for my x value, my y value is still going downward. So these are both going down. Visually, this is going to make it a lot easier than having to remember odds and evens. We'll get to that point where we won't look at a picture necessarily, but if you're going to sketch it anyway, that's going to be the easiest route to go. So when we do that on the second one as well, I'd expect that you're going to get a sketch of this one too. You're like, well, I can't find a vertex on this one because it's not a parabola. I agree. So I'm going to take a peek at the sketch, and I'm like, oh. Now, if I wanted to go to the table and get a real accurate picture, could I? Sure. Do I have to? Not so much this time. And why is that? Well, here's why. I'm looking for domain and range with this. Well, it keeps going forever to the right, forever to the left, just like my first one did. But my range also goes forever down, forever up. And since I'm only using the picture to help me out with that in the end behavior, it doesn't matter as much as it does with a parabola. So I have to have some flexibility. End behavior, and we're going to nail this time. As x goes left, I know left this time. What's happening to y? It's going down. So left and down go together. And then what happens to y as x goes to the right? Y is going up. So y is going to positive infinity. So again, you can just follow the arrows. You know, what's happening as it goes left, what's happening as it goes right, and use your infinities accordingly. And then we go a little into review mode, and we're done. So simplify each expression completely and write in standard form. I cannot have an I in the denominator. Now some of you, when you go to rationalize, have done a solid job except for one thing. You have to change the sign of your I. So for instance here, it has to be 2 minus I that you're multiplying by. Because if you do 2 plus I, the I's aren't going to go away. So as we're doing that, thank you. So as we're doing that, now we have to sit and box this out, foil this out, whatever it happens to be. So again, I'm going to save you a little bit of time because again, we've done the box enough to get most of you going on this. So if I were to box this out, let's see, we'd have first, we'd have outer, we'd have inner, and we'd have last, and we'll talk about that last here in just a second. And when I do the denominator, I got first, I got outer, I got inner, and I have last. And there's one thing I have to know to make sure this works out for me. To simplify it, I have to remember that I squared is really negative 1. So when I look at these and I say, ooh, I see I squareds, this is 2 times negative 1, which is really just negative 2. This is really minus negative 1, which makes that positive 1. And there it goes. So when I go to combine my like terms now, 8 minus 2 is 6. Negative 4 and negative 4 is negative 8 because I'm adding. Down here, 4 plus 1 is 5. And my i's cancel out. And I'm safe. No i's in the denominator under any circumstances. Can't do it, can't do it, can't do it. Solving. I'm going to write this in big letters. You have to isolate the x squared term before you can square root. I can't help it if you see a perfect square somewhere and you just want to do it then. Don't do it. Isolate x squared. Add the 8 over. I know you see the 36. You want to square root now. Don't do it. Divide by negative 3. Now we're ready to square root. But there's a couple more pitfalls awaiting us. 2 things going on here. First, it's a quadratic. Quadratics have 2 answers. So I know I have plus minus working. Also, I have a negative that I need to deal with. Take an I out. And then my last thing, and then you're going to be like, oh, I don't want to see any decimals. Oh, I see like 3.48 or something. I'm going to flip my lid. Break down the radical. Plus or minus. Square root of 4 is 2. That can hang out with I. But the 3 still is underneath the radical. I'm done. Vertex formed by completing the square. Here goes Harty on a roll. It's all about the b term. Take it, divide it by 2, square it. I would highly suggest writing this out because that's the one thing that some of you, when you were doing this on the quiz before, skipped that step. Not a step we can really skip. Because now that I have that on both sides, I can turn this into its binomial form. And again, easy way to get this number. Take the b divided by 2. If you showed it, you'll see it. And then get y alone by minusing the 16 over. In my vertex, opposite of h, opposite of negative 4 is 4. Keep that because it's plus k. Can of corn. Lead coefficient and degree. Be careful. Find your degree first. Well, why do I want to do that? Because the lead coefficient goes with the same term. If you just do lead coefficient right away, you're going to write 1. It's going to be wrong. I'm just saying. Odd or even degree. Even. Okay? And again, typically your number of real zeros is going to be your degree value, which is n. Typically your real zeros is going to be n minus 1. Now, what if I want to look, can I look at a picture and see it? Sure, I absolutely could. And I'll actually pop that up in just a second. I just want to make sure that I can chat about this last one for a second. I'll hustle back. Solve algebraically, write as an interval. Okay, first thing to remember, this is an and statement. So to find the values, I need to factor this, or I could use the quadratic formula. Either be legit. So multiply to negative 60, add to 7 would be 12 and negative 5. So my x's, my zeros, set those equal to 0. would be 5 and negative 12. Now, if some of you want to visually see this, because remember, the and statements are the ones that have endpoints and we're in the middle. So I could just look at this and say, well, it's negative 12 to 5. But if you don't remember, we talked about the ability to draw a picture like this and then test a point out, because my answer is either going to be in here or it's going to be outside. If I try 0 out and plug it in, 0 plus 0, as I plug those in, minus 60 is less than 0. Is negative 60 less than 0? It sure is. And that's where this comes from. And as some of you are strolling out on me here, I'm going to try to show you our picture of this. If not, it can be like a special flash feature later that you check out. Now, do I see the entire picture right now? No, which is why sometimes a formula can help me out some. But I'm looking for change of directions. I see positive to negative. There's 1, 0. Negative to positive. I see another 0. And then I see it going. So am I going to necessarily be able to look every single time and determine it that way? No. A lot of the times I can do it, but it won't be every time. Watch your graph. Otherwise, look for changes from positive to negative. That'll do it. And that'll do it for us. See you tomorrow.